that. So now we're going to start revolving. Everything else is revolving. I'm going to have some plane region. Okay? And my cross sections are going to be circular. And I'm going to get this by revolving that plane section about some axis. The question that I have to figure out is, when I go and do that, is there a gap that's going to happen between my axis of rotation and the region? In this picture here, I have a region that I'm going to rotate about the x-axis. When I do that, there's no gap. I'll have a solid disk. When I go and rotate that, my cross sections will be disks. And so I'm going to have the same kind of setup that we had with the cross section from previous, but the cross sections are circular disks. Okay? And so the name of this method is called the disk method. If you have a gap between your region and the axis, we'll have something totally different. When there is a gap between the region and what you're rotating about, then you don't have a disk. It's kind of like you have a disk with an inner disk taken out. It's a washer, they call it. And so it's a different method. Not much different, though. Just the way the formula works out is slightly different. Okay? If you can get the first one, I'll show you something that will help you understand the second one, and it's not as bad. You just got to know which one you're going to end up with. It's going to be important that you get a good picture to start out. Without the picture, you don't know if there's going to be a gap or not. So there's some function that we need to know how to graph. That function there is the root of x. We need to be able to graph the root of x. Okay, I'll blow it up and we'll work that problem out. This function here is y equals x, and then x equals the root of y, which is just y equals x squared. There's some basic functions we have to be able to graph, and our inability to be able to graph them is going to haunt us in the very, very beginning of the problem, because we won't know how to start. If we get a good start of the picture, then we can figure out what the formula does. So here's what's going to happen. I'm going to have these cross-section circles. Circular disks. What does the formula say? You're supposed to be able to just find the area of that disk. It really is a cylinder. It's the cylinder that we're used to. It's a right circle. Pi r squared times the height will be the area of that disk. And so the radius, though, will be something that we have to find. The radius is going to change. You tell me what x is, I'll give you a different radius as I move that from some beginning x to some ending x. And so that's the setup. I'm going to have cross sections that are circular, and the area of those cross sections will be pi r squared. Okay. And the r is going to depend on what x is. Okay, let's go work that problem. And then the volume will be just like we had before. Find the volume by taking the integral of that a of x. All right. Do I have the picture? Yeah, here's a bigger picture. So, so I have this y equals root x function, and the question will be described like this: take the region. Take the region bounded by the curves. Bounded by the curves y equals root x, x equals 1, and the x-axis. It's up to you to take this and decipher that they mean exactly this shape. You have to know what y equals root x looks like. You have to know what x equals 1 looks like. You have to know how that interacts with the x-axis and identify exactly this shape. Okay? And then rotate about the x-axis. You don't have to know the 3D shape. I don't really care about the 3D shape. Okay, but we're going to find the volume of this bowl, the solid bowl. We have the interior as well. We're going to find the volume there by setting up this formula right here. Okay, what will be the radius of the circle? The radius of the circle is just going to be the distance up to the function. Starts off small, and gets larger and larger and larger. By the time you get to 1, it's at the largest it possibly can be. What is that distance? It's this distance up. It is y. It's root x. The radius is root x. Okay, when you're doing disk method, all you need to really find is the radius and plug into this formula. What's the A? What's the B? The A is where you start at. The B is where you end at as you move that to create the volume. Okay? I need to show you some animation, some 3D pictures that shows, you know, the actual volume being swept out, but that's the idea though. Okay? So what's the formula? Pi, the integral from 0 to 1, where I take the radius, which is root x, and I square it. Not bad at all. Square root x, you get x. So the volume of this shape is pi. Why is pi a part of this? Because it was part of the circle formula. What do we do with it? We just pulled it outside, that's all. Just like we pulled the 4 outside in that previous problem. So pi comes outside. Pi is a part of this now. Pi wasn't a part before because we didn't have circular cross sections. Now pi is a part of it, and you just need to integrate x. What's the antiderivative of x? X squared over 2. So that's a half. Minus 0 times pi. So the volume of that shape turns out to be pi over 2. The volume of this shape is pi over 2 units cubed. Using the formula for disks. It's a disk. It's a solid disk. We had our region, we had our axis, there was no gap between our region and our axis. When we go and revolve that, we get this bowl shape, solid bowl, and we get the volume of that shape by using that formula. Okay? Not as bad as the other technique of cross sections where there was no revolving around any axis. Questions on this example? Yes?
How did you get the radius equals root x?
Okay, so I guess it's a visual thing. You have to picture, as this thing moves, this distance here is exactly the radius. Okay, what is that distance? It's the distance up to the function. It's going to change, right? Here, the radius is a smaller distance. It's the distance up to the function. By the time you're here, it's going to be a radius of 1. You know, this is a disk. This is a circle. It's flattened out like this, but it's a circle with a radius of the height up to the function. Whenever you try to find the distance from the x-axis up to the function, that distance is y. It's the f of x. It's the function height. And so in this particular case, the function was root x, so that was our radius, root x. It won't always be the case, and we'll definitely make this more difficult. This is for our first example. This one is on the easy side, definitely.
So
More questions?
Given that the function was root x?
You're given this. The question will be phrased. I'm sorry, it's just a bunch of. I mean, there'll be a nice sentence written out, but basically that's the question. It's your job to go from question to picture, from picture to not 3D picture, but from picture to formula, and then formula to the answer. Okay. All right, great. Wonderful. That wasn't that bad. Okay, so that's the fancy written up way. Calculate the volume of the solid generated by rotating the region between those curves and the x-axis. And so there it is worked out. We did it already. That's just a formal writing up of the problem. Okay? Sorry, I just did it on the side here because we had this room available. Here's the formal writing up of the problem. Okay? That's disk method. Here's another. calculate the volume of the solid generated by rotating the region between the curve y equals 4 minus x squared, y equals 0, and the x-axis. We won't even be given what's underneath here. We won't be given these shapes. From the words, we get the picture. From the picture, we get the formula. From the formula, we go and calculate the answer. That's how it's going to work. You have to know what this looks like. 4 minus x squared. It'll be your job to know that that's a parabola that opens down, and it has a maximum height of 4. Maybe even to know that when it hits the x-axis, you're at minus 2 and 2. All from that formula. It's pre-calc. It's shifted up 4, and first it's reflected about the x-axis, and then it's shifted up 4. That's what's done to the y equals x squared normal parabola. Y equals 0. That's just a fancy way of saying the x-axis. And we're going to rotate this about the x-axis. So words to shape, and then from shape, it's up to us to get the formula. We recognize that when I go and revolve this around the x-axis, I'm not going to have any gap between my region and my shape. I'll have a nice solid disk. I need to find the radius of that disk. So this is what the 3 is like. It looks like a bead. Who cares what the 3D picture is? But that's what it is. And that's going to be the radius there. So there's going to be a disk. I'm sorry if I don't draw it, but there is a disk here. There's another one that comes down here. La, 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 la. And then this guy comes down here. This represents a disk. And this guy is the radius of that disk. Okay? How do I undo that? Erase everything. Okay, there we go. All right, so what's the radius? It's, once again, it won't always be this. Please don't assume this. It won't always be this. In these last 2 examples, the radius was the distance up to the function. Not always. But here it is. The radius is 4 minus x squared. What's the formula then? You're supposed to take to find the volume, pi r squared, and integrate it. So you're supposed to take 4 minus x squared and square it. And you're supposed to go from what to what? What does this move from? This moves in this direction from minus 2 to 2. Now here's where mistakes creep in. You've done all this setup wonderfully. 6 points just for that. The 4 points at the end, or the mistakes are going to creep in. You're going to mistakenly call this 16 minus x to the 4th. You're just going to square each one, right? Square the 4, square the x squared. Fine. Right? No. Please don't. When you square something that's multi-term like this, there's some middle terms that you'll be forgetting about. Squaring something is multiplying it by itself. There'll be a middle term you'll be forgetting about. If you have to take 4 minus x squared and multiply it out by itself, there's a middle term of minus 8x squared. Yes, you'll have the 16. Yes, you'll have the x to the 4th. But you'll be forgetting about the middle term, 8x squared. Okay, and yes, there's the pi outside. And yes, you're going from minus 2 to 2. Okay. So be on the lookout for minus a to a. It's a gift. Not that you have to, but it's a gift. Take advantage of it when you can. It won't always be this, but here it is. That here I have a function that is even. How can you just look at the polynomial and know that it's even? I have even powers and a constant. What does even mean? Even means it's symmetric with respect to the y-axis. Not this picture here, but in the end, this formula here has a graph that is symmetric with respect to the... It doesn't have to have a constant, but it could have also a constant. So that's an even function. And so instead, we'll save ourselves some work, and we'll double going from 0 to 2. You don't have to. Please, if you don't like that at all, don't do it. It's just a gift. Take advantage of it.
So is that just when the like numbers of the interval are the same, even though the sign isn't? That you can take it to the outside? That wasn't a clear question.
The numbers.
So okay, so you say like -2 to 2, and then you pulled one of the 2's to the outside.
Oh, I didn't do that. Okay, I got you. Okay, this doesn't have, it could be -3 to 3. The point is that whatever the shape is, on one side it's the same shape on the other side.
Right.
So doesn't matter about these numbers being even, doesn't matter about coefficients being even. Even technically means that when you put in -x for x, you get the same thing back out. That's technically what it means to be even. Here's a shortcut to what it means to be even for a polynomial. And when you are even, you're allowed to pull the 2 out. I didn't take this fact that it was a 2 and pull this 2 out. I just doubled. I didn't want to find A1 and A2 to get A3. I wanted to double A2.
Thank you.
Yeah. So double, not that 2 being. It's just a coincidence that lots of 2's and lots of even numbers going around. I don't want you to be misled. Okay, so 16x, 8x cubed over 3, x fifth over 5. That's my antiderivative of each one of these guys. Using the fundamental calculus, using the power rule in reverse. Now what do I evaluate from? 0 to 2. This is why I did it, because I didn't want to have to plug in a -2. It's bad enough I have to plug a 2 in. I didn't want to also have to plug a -2 in. So since they gave me this way out, I took it. So now I plug a 2 in, and I get 32 minus 64 over 3 plus 64 over 5. See how the end of these problems can get bad? We have to put these fractions together. Okay, if you make a mistake there, I'm only going to take off 1 point. Who cares if whether or not you can really put these fractions together? In the big scheme of things, I care that you can set it up. And you can set up the integral and work out the antiderivative of the integral. At the end, okay. Questions? Yes?
Are you able to do the symmetry in terms of the triangle?
In the end, it's not the picture of whatever's going on, it's the formula. In our formula, it wasn't that the triangle was an even picture, even function. It was that in the end, whatever we were integrating was even. Okay, our setup was not even at all. That triangle is not symmetric with respect to the y-axis by no means. It wasn't that. It was in the end, your actual integration was of a function that was even. Yes. Okay. That was on purpose. Thanks. Okay, I'll let you finish it out. Here's what it looks like when it's finished out. So you put it together. I see 32, I see 64, I see 32. Something screams at me. So I take advantage of it. You don't have to do it. But I would factor out a 32. It's like yelling at me to do that. Seriously. I much rather would deal with 1 minus 2/3 plus a fifth. I can handle that. 62 to 34, 34, 32, 64, it gets in the way for me. So I would factor out a 32, and I could deal with that. Since they gave it to me, I'm going to take advantage of it. Not every problem's going to have this, but when it's there, it yells at you. You got to hear it. Okay, 1 minus 2/3, that's a third. a third plus a fifth, 8/15. Okay, so I have 64 pi times 8/15. So I can do that. Whatever 64 times 8 is. 120. 512? 512? Okay. So see how it gets bad at the end, but most of your points are going to come from the setup. 6 points for giving me this. 3 points for giving me pretty much this. And 1 point for finishing out. And it just so happens that in these last two examples, the radius was always the height of the function. It's special because it was the x-axis and the function was graphed in a certain kind of way. Not always going to be that. Please don't assume that. Okay. It doesn't have to be always that you're rotating about some axis that is horizontal like this. It could be that you're rotating about an axis that is vertical. What happens then is that you're just changing the variable. Instead of being in terms of x, you're going to flip it. It's going to be in terms of y. Your function is going to be some formula based on y. Same setup, same formula, just different variable, that's all. If I take this region here between these curves and I rotate about the y-axis, then my cross sections are discs, yes, but they're disc in terms of y. I'll take that and I'll move it upwards in terms of y. So you're changing the variable. When your axis is vertical, you're in terms of y. When your axis is horizontal, you're in terms of x. Let's go do that problem. It'll be written like this. And it's your job to get the graph. Okay. It'll be written like this. You'll have to know what y equals x cubed looks like. You have to know what y equals 8 looks like and x equals 0. You have to take those and graph them. Y equals x cubed looks like that. Y equals 8. Horizontal line. X equals 0. A fancy way to say the y-axis. So then you denote that this is your region. Words to picture to get the region. Now, rotate this region about what? About the y-axis. There's no gap between your region and your axis. When you rotate this, you'll get a solid disk. That solid disk will have a volume that it's up to you to find, and it'll be this distance as the radius. That distance there is an x distance. The distance off the y-axis is an x. Distance off the y-axis is x, just like the distance off the x-axis was y. Okay. We have y equals x cubed. I need x. So I take the cube root. That's going to be your radius. As y changes, you'll have a different radius as you move that vertically upward. So your volume is going to be the integral of a of y dy, which is pi r squared. From some a to b. So it's going to be from 0 up to 8. you need to take the cube root of y and square it. Algebra, cube rooting, and then squaring. Y to the 1/3 power, and then squaring. Y to the 2/3 power? The integral, don't forget the pi, sorry. Pi times the integral from 0 to 8 of y to the 2/3. It's all in this setup. This part at the end is not as much. Getting this, 6 points. Integrating this, 3 points. Final answer at the end, 1 point. Power rule in reverse. Supposed to add 1 to it. What is 2/3 plus 1? 5/3. Instead of dividing by 5/3, times by 3/5. Don't forget the pi. And go from 0 to 8. Uh-oh. 8 to the 5/3 power. Okay? I didn't notice till last semester. A student told me this. Pretty neat. I would take the cube root and then take it to the 5th. Student said, you know what? Just do it this way. Take 8 and rename it as 2 cubed. Because then you'll just cancel out the 3's. When you raise something to a power, raise to another power, you multiply. So that cancels out the 3's. So you get 2 to the 5th, which is 32. So here's what you're looking at. 3 pi over 5, 32. So the final answer is 64 pi over 5. 96 pi over 5, sorry. Whatever units we have, cubed. That's the volume of that shape using disk. Okay, one more, and then we'll take a break. I'm sorry. Where did what? Where did 3 come from? Where did 3 come from? Where did 3 come from? Where did the 3 come from? 3. Oh, 3? I see it now. 3? When you take to the 5/3, you're supposed to divide by 5/3. So we multiply by 3/5. One more, I'm sorry, but I just want to cover all bases here. I just want to be thorough. I want you to see all different kinds of possibilities, okay? So we have to do one more, and then we'll take a break. I keep saying that. And once again, you're not going to be given the picture. So I shouldn't even have the picture on there. In fact, let me take it away for a second. Oh, that one too. All right. Okay, here we go. All you'll be given are these words in those formulas. What's different about this one? You're going to be rotating about something that's not an axis. Our first one was the x-axis. Our second was the x-axis. Our third one was the y-axis. I don't want you to be deceived and think it's always going to be that. And so here we're rotating about a line that's x equals 2. We have to know the graph of this function. These other guys are just vertical lines and horizontal lines. We have to know what that looks like. 1 over x minus 2. Okay. You have an issue at 2, right? If x is 2, you'll be discontinuous. At 2, you'll be discontinuous. Okay. And the function is going to look like, as you approach 2, it's going to get very large. And it's going to get smaller and smaller the further away you move from 2. Okay, there's another side to it. Yes, we're not going to need that. And it's going to approach 0 as x gets very big. X equals 2. That's a line. X equals y equals a half is a line. And y equals 4 is a line. So here's y equals a half, say. Here's y equals 4, say. And here's x equals 2. Bounded by these, I must be talking about this region right here. And all of that is up to you to get. All right, let me go back and now put the nice drawing in there. I just want to take you through that process of getting that. If I can, paste. Okay. Oh no. All right. Shoot. Undo rocks. Okay, here we go. So we have that picture, and we're rotating about the line x equals 2. So see how it's flush up against there? We're going to have discs. What kind of disc? In terms of y, what's the radius going to be? It's not going to be easy. Not going to be easy. That's the whole purpose why I did it. The radius is hard. The radius was kind of easy for those other ones, relatively speaking. This radius, hard. What in the world is that distance? It's not off of the y-axis. So we can't just say it's x. It's not off of the x-axis. So we can't just say it's y. How do we find that distance? Because that's what the radius is. I go and revolve, and I have this shape, and it's a nice disk, and that's the radius. How do you get that distance? Okay, so we start off kind of easy, a little more difficult. I think this would be the hardest. When you start moving a line that's something other than the x or y axis, finding the radius is the hardest part of the whole thing. The distance changes as you move upwards from a half up to 4. This is a half, and this is 4. The distance changes. Our job is to figure out what that distance is. Suggestions? Yes?
You pretend it's y equals whatever x when it's given the original.
Okay, I'm with you. If it was y equals 1 over x, the shape would look like that. Okay, and this is the y-axis. Okay, I'm with you. And it would be this distance here. Okay? Let's get started. Okay. Okay. I'm going to tell you that it's the difference between two distances. Yes?
Would you maybe do like minus, do what you usually do, but then minus 2?
Very good. That takes these two approaches, and it takes and puts them together. So here's the distance off the y-axis. That's what that is. We said that is called x. Right? We subtract from that this distance here. That distance we subtract is going to be the same thing as we move up and down. 2. So the radius is equal to x minus 2. So we're going to figure out then that it's just like if it was the y-axis, except for you did some kind of shift on it. Okay? You moved it over to the right 2, you need to be taking away 2. It's both the ideas together. Okay? Here's the problem though. We have x, and the formula is going to be in y. our formula is y equals 1 over x minus 2. I need x equals
1 over 1.
Okay. How do you solve this guy for x? It's kind of like 1 over y. Let's say that x minus 2 is 1 over y. Yes. You okay with that? A over b equals to c. You can switch the b and the c. Cross multiply. We're good. And then divide. We're good. Okay. So then what's x? Very good. Exactly what the guy was saying there. It's like 1 over. It's like the 1 over. Then we're gonna have to do something with it. So anyway, here it is. This is your radius. Wow, that was tough. That's your radius. 1 over y plus 2. We go over here. We figure out what that is, and we come up with this. The formula is not difficult. Remember the formula? The formula is just square the thing. Okay, take r of y and square it, integrate with respect to y from some low point to some high point. Don't forget about pi. Okay, we're going to stop at the setup and then take a break. 1 over y plus 2, the whole thing squared. From what to what? What's the low point? Half. What's the high point? 4. Okay. Yes, this was minus 2, but here's how we go and figure out what we just got. See what I'm saying? Like, yes, it was minus a 2, but then what happens was that we needed to later take a... Oh, wow, look at that. Never took into account the minus 2. Whoa. Y equals this, so x equals that. So x minus 2. Oh, yeah, how about that?
So it's just 1 over.
Oh, that's convenient, right? Wow, that's beautiful. X is 1 over y plus 2. We never subtracted 2. Boy, that's really nice. That wasn't on purpose. Yeah. Okay. Take a break and let you chew on how to integrate that. Okay. I'll finish it, and we'll just talk about it when we get back. And so we have the distance x, 1 over y plus 2, minus the distance 2. We end up with 1 over y. It's our job to integrate 1 over y squared. Don't think of that as being a log.
Sorry. Ignore me.
It's not a log. We can treat it as y to the negative 2 and use the power rule in reverse on it. It's y to the negative 1 over negative 1. And so when you get y to the negative 1 over negative 1, that's the same thing as saying negative 1 over y. Okay, we have to put a 4 in. We have to put a half in. Oh no, we let it back in. Oh well, I can't do it right now. So we put a 4 in, we get negative 1/4. Be careful when you put the half in. So we get negative 1/4 minus negative 1 over a half. So see how that becomes a positive 2? So 2 take away a 4 is 7/4. And that's why we get the answer of 7 pi over 4. Okay, so the radius was the distance to the function, take away the distance to the axis. That's how we end up with x minus 2. We have to take away 2 to get this radius distance. All right, and then that is the end of our notes on disk method.